This tutorial shows you how to use component matching to automatically check for discrepancies between models. We're going to start by talking about why we compare models. That's going to lead into a discussion on how component matching versus clash checking. Then we're going to dig into how Visicon's component matching works. And then we're going to conclude with some project examples. By following this tutorial, you will learn how to apply the component matching operation and understand its configuration options. Why do we have to compare models? That's because we realize that design projects rely on an array of different models. We start with an architectural model that develops into a parallel structural model, and each structural model, or the structural analysis, then has its own various models. Once you're done with construction documentation, then the fabricators each create their own individual fabrication models. So let's assume the architectural structural models were developed in Revit, the analysis model is ADAPT or is an ETABS model. Then here with the fabrication you would have a Tekla structure steel model. And then the contractor eventually comes in, assembles everything, and is really focused more on constructability. So stepping back, we realize that the architectural and structural models really have the same intent. So they're trying to represent similar things. Likewise, the structural and analysis models really are expected to represent the same intent as well. Also, when you go into fabrication, let's say the steel fabrication shop drawing model has to really represent what the engineer had outlined in their Revit structure model. Likewise, it could be a situation where the actual members that are being designed or modeled in the Tekla model, really the actual detail designation actually resides in an analysis model like an ETABS as opposed to in the Revit structural model. So really it's a matter of kind of understanding that we have all of these different similar design intents and we need to be able to keep all of these models in sync. When it comes to the contractor though, what you have is they're primarily focused on clash checking. Right, so they're not as concerned about the actual attributes of the components. They're not concerned about the necessarily the design intent of the components. They're just assembling the various discipline models and making sure that everything can fit together from a geometric perspective and are just doing clash check. I would say in a classic term, that's what mostly is understood as BIM, right? Clash checking, bring components together. Do they fit? Do they not fit? Really what we're talking about here is on the upfront side of the design or the design side of the process, where we're really trying to automate the process or streamline the ability for different designers to be able to come in and be able to match the design intent that is represented in various different models. And I'm not sure programs like Navisworks or even BIM 360 that do coordination really get into the level of the properties to be able to identify specific design intents that you're after. So in conclusion here, what we're trying to look at is recognizing that we have all of these differently developed models and trying to keep the actual design intent parameters consistent is pretty challenging. And that's really where Visicon's component matching tool comes into play. So how does it work? We start by merging any two discipline models. So here we're going to go with an example where we're taking the analysis. This could be an ETABS model, and we're going to merge it with the Revit structure model. Once you've merged the two, you would go in and you would apply a new operation. So Visicon has this notion of these operations. These are things that automatically check your model. The classic ones that I refer to are clash check, find duplicates, clearance check. So this is what all BIM tools do. What's unique for Visicon are the three Boolean difference, variance checking, and component matching. Component matching is new, and that's going to be the focus of today's tutorial. Instead of going and applying a new component matching operation, you have the option of applying a previously configured and defined template. So we do give you the option to go and save templates with all of your rule configuration and operation configurations and just open a new model and just apply those. So that'll be covered in a separate tutorial. So how does it work? So the way we look at the world is we say dealing with matching design intent, really we're trying to identify components that are supposed to represent the same thing in different models. Now they might be represented differently, but the underlying intent is the same. So the first thing we do is go through kind of a pairing step. Once we've paired sets of components, then we run tests. So it's constantly this process of pairing components and then testing them. So how do we do our basic testing? Our premise is based on the fact that if components are intended to have the same intent, most likely they're modeled in the same space. So you can think of this where we're leveraging the classical clash test to be able to identify the first set of paired components. We're not calling them clashes. They're just simply paired components. So we kind of make a note of those that are pairing. But there are cases where you have one model, let's say the structural model, you only have pure structural components like columns, walls, slabs, and those types of things. Whereas you're matching it with maybe an architectural model or another model that has a whole bunch of other types of component types in that same space that could be overlapping with a beam in the structural model. So the first way that we allow you to kind of refine the pairing is to be able to restrict the comparison to those of similar category. So either none says it doesn't matter as long as there's a component occupying the same space in model A and a component in model B in the same space, then let's try to pair and match them. Otherwise, limit it to category or by type. Type is more specific than category. Then the next thing we do is we went through, and this is based on going through hundreds and hundreds of client models and working with them, and we realized that sometimes at really, really early stages of the design, two components might still be too far apart, so they're not actually touching. So the initial pairing algorithm is not picking them up as being paired, but we do want them to be compared. So in this case, you use the first configuration option, which is called minimum contact clearance. By specifying a positive distance, the left image would pair those two components even though they're not touching. The middle instance was another scenario we were running into where you actually have closely packed components. So for example, here are these two members. So they're close enough so they're touching, so they would in essence trigger our first criteria for pairing, but we say they're really not close enough, so we want to ignore those. So in that case, we use the second configuration option, which is called maximum allowable penetration. And in that instance, you're allowed to specify a distance for which, if there's an overlap, the pairing gets ignored. Then we go to the case on the right. We found many scenarios where we have linear elements, for example, columns and beams that are touching end to end. We don't want to compare purple column or member against the gray one because they're just touching end to end. We only want to limit the matching to those that are really on top of each other. So in that case, you would use the maximum allowable penetration at extremity option. So you can specify a distance of allowable overlap at the ends, and the matching is ignored. So let's move on to the next configuration option. Once we've configured the pairing, the next step the program goes through is it tries to identify what we call orphan components. So orphan components are components that didn't meet any of the prior pairing criteria. So in this case, we're looking at a column here that is just completely unmatched. It only exists in one of the models. Everything else that's green is already matched. So this is a very important, critical first check when you're comparing these models, and it easily highlights components that are completely standalone. And this is not possible to do in clash checking because those standalone columns, in theory, touch the walls and slabs and other members. So they would clash with something, but we're just trying to isolate component types that are isolated and on their own. So those are orphans, and those will be pretty important. Next, we can go and we're starting to now define specific design intent criteria. So here our first design intent is that we expect the columns or members in one model to be aligned or in the same exact position as those in the second model, right? Makes sense, right? My structural column should be in the same place as my architectural column, should be in the same place as my analytic model. So in this case, you would go in and you would set the centroid tolerance. Again, we're going to run through this in the actual project examples, but here you would come in and just modify the centroid tolerance to a limit that you want. The second test that we're going to go into is say that there's a second design intent, which says you want the same member size. Well, we found that one quick way to be able to test for this without going into the details of what the member naming actually is, because we're using this to compare, apples against oranges, or pineapples against apples. And so these are totally models created in very different systems, or even if they're created in Revit, one person is creating it with certain attributes, and then the other one completely separate attributes, even though they're the same program. So here we found that being able to run a test off of area tolerance is very useful. What this is flagging are components that are aligned in the right place, so that the alignment intent has been met, but the area, the cross section is off, and it requires attention. So you can set a tolerance for your area. The last rule that we're going to look into, and there are others that we're not going to cover in this tutorial, but these are the three primary ones I wanted to go over. So this is where you're checking the matching design intents between two components and two models based on an expression that you write. One of the things Visicon is most known for is the flexibility with which you can manipulate and work with all of the component variables and express their behavior in terms of these expressions. We've extended that now to allow you to write expressions that are in terms of the components in Model 1 against Model 2, or in this case, Model A versus Model B. So what are we looking at here? Here we said the design intent was really the top of the components in the two models were expected to be at the same elevation. I'm going to just simply automate that check by saying that the upper bound, so the Z top bound of my beam in one model, should be equal to the top bound Z in the other model. It's that simple, but very powerful. This can run in seconds through thousands and thousands of components and identify exactly those that are mismatched. Now that we've gone through basics of how component matching pairs components, and then went through some of the fundamental tests that you can set up, right? We talked about centroid, area, and expression. The question is, so how do you know where things pass or fail? So what's great is once you run the operation, it color codes the model and highlights each of the affected components based on three criteria: whether it passed, whether it failed, or whether it's an orphan. You can then go in and determine which subset of those results you want to have displayed on the model. And then lastly, you could say, well, that's great that I can visualize it in the model. I want to produce a report that I can hand off to other project stakeholders so that everybody who's responsible for certain components can come in and make those changes if necessary. So here we'd go into the actual reports, run an issue summary report, and on the right side here you see a nicely formatted Excel spreadsheet that then can be used to document the exact changes between components. So let's dive into a project example. So the first example we're going to go through is this simple office tower project. I've skipped the phases of merging the models. As you know, any component that I select, I have access to its properties on the left. And under the project browser, you can see here under the models tab, I can see that I have two distinct models merged in this Visicon instance. I have one that's called ETABS model and one that's the Revit structure model. Even if I color code and zoom in, it's really hard, as you can see, to see exactly what the difference is between the components. This is one perfect example where if I run a clash check, I sure hope that 99.9% of these components in these two models should clash. So there's nothing your clash detection in other BIM tools can do to help you in this situation. We need to be a little bit smarter about it. So let's go ahead and explore that. So we're going to go to Operations. We're going to go to here. And like I said, we have the three unique Visicon ones, which are Boolean difference, variance check, and we're going to dive into component matching. So we've created our component matching operation, our first one. You see operations can be accessed and configured here through this tab right there. And so the first thing we're going to do is just say, we're going to run it for orphans. And we're going to take this and we're going to do absolutely nothing except for run this for orphans. And we see this operation has already been pre-configured to check as model A, the ETABS model, and as model B, the Revit structure model. We're changing absolutely nothing else, and we're just going to run this. So now what we've done is looking at the model, and again, under our subset of results that we want to show, we're showing all. So we're showing the matched and paired and passed components as green, orphans as yellow, and any failed would have been orange, but we haven't set any tests yet, so that's why nothing is orange. So in this case, we're observing this model, and this is a very powerful visualization of your model, which you may not recognize. What this does is it clearly highlights individual components that are unique only within one of the models. So in this case, I can quickly see there's potentially a problem with these two columns right here. I can verify that by going to my models view. I can see that, if I turn off one of the models, there you go, right? So in one of the models, this Revit structural, I only have a column on the left side. And if I turn on my ETABS model, the model is here. So somewhere along my last design phase, somebody made a change, and that was not properly propagated throughout both models. So that's a fundamental issue that the orphans allow you to identify. Remember, Visicon has all of the color settings. So you can see here, we're under the model color mode. I'm going to switch over to the issue color mode. Whenever we're looking at the results of an operation, like this component matching operation, what we want to do is we want to be in this issue color mode. In summary, we've identified this, and we can clearly see where we have components that are in one model and not in the other. Much clearer description or presentation than if you just merge and change the colors. Let's now zoom into this corner here, and we say, okay, really this column and this column should be matched for testing, same as these, right? So here you can see there are two columns, if I zoom in closely, that are close enough and they were paired. These two were paired because they actually touch, whereas these did not touch. So the first thing we're going to do is show you some of those modifications to the pairing. So we're going to clone this. So I'm going to call this orphans, and we're going to say increased tolerance. And I'm going to come in here, and under my maximum contact clearance, I'm going to say 6 inches. Rerun this. Let's see, 6 inches was not enough, and that's probably because if I zoom in here and look at my measure and look at a clearance, I can see that it was exactly 6 inches. So I need to go just a little bit over 6 inches. So let's test that. So if we go into even 6.5 inches, so I go 6.5 inches, rerun this, and we see now those are paired. So all that is telling me is that when I run my tests, it will now test against the properties of this component against this one, even though I know they're not overlapping. These two will be tested, and those two, I'm using tab to jump between those two, and even those two will be tested. That's exactly how this works. Let's go under operations. We're now going to create a new component matching. And we keep turning off the previous one so that we can focus on just this one. The next one I want to do, columns, Centroid alignment. Right, so let's say I'm only interested in checking the design intent for those. We're going to keep everything above the same. We're not going to bother with this minimum clearance. We're going to come in here and we're going to limit the input to select components. Here we're just going to say we only want to check columns. I always recommend run each component type separately. It just makes the data much easier to understand, right? So keep your columns separate from your slab checks, your beam checks, and your wall checks. So here we're only going to run columns. We only want to see those that have failed, and we're going to come in and under our Centroid tolerance, we're going to start by specifying a 2-inch tolerance. So I just put in 2 inches, and we're going to run this. So we have 503. So what this is doing is now it's highlighting all of those columns that don't meet our 2-inch criteria, right? So you see this one, corner one is gray. That has met our criteria. These have not. And so if we zoom in, we can actually see, yes, in fact, there is a little bit of an offset. And if you're interested to see what is the offset for each of these identified pairs that fail, it's created an issue. So if I go to the issue, and we're going to go to home, and we're going to auto fit. So we're going to say, oh, there's a pair of columns right there, right? So we see those are mismatched, and it tells us exactly that the mismatch, their centroids are off by 3.2 inches. We had set a tolerance of 2, and we've exceeded. And so here you can see this one has a distance of 3.6 or 3.6, 3.2 and so forth. So this is how you can come in and see exactly what's going on. We're going to go back to our list of operations and let's call this one 2-inch tolerance. We're going to now clone this one and we're going to check and say, well, we're checking our ETABS against our Revit model. Let's say 6 inches is something we can live with, right? 2 inches might be too strict of a tolerance for that purpose. And so here we will only want to identify columns that are more than 6 inch off center because those we want to correct because we believe any discrepancy in our ETABS analysis model that is greater than 6 inches may actually have an effect on the design. So we want to find those. So we're going to come in, we're going to now switch this from 2 inches, switch it to 6 inches and rerun. So now we have only a subset of the columns that don't meet our 6-inch criteria, and you can clearly see they're too far apart. Again, we go to our issue. We can select any of these, and we can see definitely column C7 and column 18 by 28 here. These are off by 20 inches greater than our 6 inches. I had addressed how do we actually display or export this information into a report. We're going to go to Reports, New. We're going to go into our Issue Summary Report. And we're going to scroll down and we're going to limit the writing of the report to only this last operation, which was column centroid alignment 6 inches, and run this report. So you either run it by right-clicking, running here, or with the report selected and then the reports ribbon above, just hit run. This now creates a nicely formatted Excel spreadsheet where you can see each of the columns that are mismatched are shown. And if I scroll to the right, it gives you all of the information that you need. And you have the option in the configuration of the report to show any additional properties. I can choose to have, let's say, the Revit ID or any other property that is available in those models can be reported out here by simply adding this variables to show. Simply add that here and it will be listed in the report. So that is how we would check the Centroid tolerance. Let's now go to the operation and we're going to clone this again. And this time we're going to say column area check. So we essentially have the same. We're going to zero out. We're going to ignore Centroid tolerance and say we're only interested to highlight places where we have a 5% difference in area, cross-sectional area. And we're going to run these. There are 30 of those. Again, a completely different set of components that have problems. So here it's now these happen to be misaligned and have a cross-sectional problem, but they could be also just columns like I believe here. Well, even these are slightly misaligned, but they could be fully aligned, but they just have a problem with their cross-section. Let's validate this. The programmist Visicon is telling us there's a problem here. Do we in fact have a problem? Let's check it out. This is a 24 by 36, and this is an 18 by 3 feet. So definitely, you see this is 18 inches, and this is only, and this is a 24. So there is a problem. What this does is allow you to very quickly identify issues that you have or discrepancies between two models that are created separately but are expected to represent the same design intent. So let's close out of this and move into another project. And so this one has some more advanced rules, and we're going to use this one to show the expressions as well, just so that you can get a flavor of how that works. So we're going to go into the models, and you can see we have two models in this example where we've merged a structural Revit model with a Tekla shop model. So here with a structural Revit model, this is a, right, you can see it's just the structural model. And if we look at the shop drawing, it's a little more simplified, but it focuses on the details of the actual steel members that are going to be fabricated. Our objective is to automate the identification of potential discrepancies between the Tekla shop drawing and the Revit structural. So we're going to go, and I've pre-configured this one. So here we have several operations, and to simplify, I have operations that are set up to check columns and some that are set up to check beams. To help the presentation of the data, I'm going to go to my visibility, and I'm only going to turn on beams to begin with. Just like we did in the previous model, if I just turn on my orphans, all this does is just highlight those components. So this member is in one model, but completely unassociated with another one. These smaller members are another example where I can come in here and say, okay, that makes sense because these are only in my Tekla structural, my shop drawing. I would not expect these to be in my other model, so that's fine. So this is a great way to validate that. Then we're going to go and look at the beam X section name. So here we're looking at the beams in one direction in the X direction, and we're going to do a matching between section name. How have I defined that? Remember, I can come in here and let's actually zoom in to a component. If I zoom into a component, I can see that in one, it's a description. So I have in model B, it's the description is the section name. And in the other one, so if I hit tab, so this is, let's see, there's another, okay, I have one of my models is turned off, so that explains why I didn't see the second member. So here we see there's an error session here. So we click here. In one of them, it says description is where the section is. And in the other model, so if I go to the other model, it's in the name, right? So this is a classic example where we have two different modeling systems. Each is referring to the actual design intent, right? So the design intent here being member size. In one it's called description, and in one it's name. Not a problem for Visicon's component matching, because here we can see that I've written in simple expression that says model A, it's the name property, right? So that's here, model A being my Revit model, has to equal the B description, right? So it's that simple. How would I create something like this? I would come in and I'd take the property, right click, copy the variable, and just come in and just say, type in A dot, and then paste in the variable, right? So it's that simple. But let's run through this. So we've gone here and let's look to see what we've identified. It's telling us we have a mismatch based on the section type. And you see we actually identify and found three members. Here we have this member, it's a 16 by 45. Its mismatched pair is an 18 by 35. So there's clearly a problem. So to understand what's the nature of this problem, we go to our model breakup and we can see, let's turn off and look at the Tekla structural model only, and we see that one is actually correctly only has one member and it's a 18 by 35. If we turn on the Revit structure model, we see that there's a 16 by 45 and an 18 by 35. So in other words, by mistake, somebody has a second member. You probably would have never found this in there. Clash wouldn't have helped. None of the other checks. You really need to be specific and identify issues like this by drilling down into the actual property names, right? So this is the issue we've uncovered, which is a hidden element within another one, right? Because it's actually inside of the other one. And if we go to our issue mode, I'm going to turn on both models again, and into our issue mode, you can actually see that one of them is ghosted, right? So this 18 by 35 was correctly paired with the other 18 by 35. It is this 16 by 45 that is triggering the failure because that was paired with a mismatched, one of the paired mismatched components in the other model, right? So this is a perfect example of where an issue was found. We can go look at other areas that are highlighted. So here we have two channels. We wonder why are these highlighted. We click here. This is a 6 by 4 by 5/8. This one is a 6 by 4 by 3/8. Again, major problem, right? You would have probably never caught this, but this is a clear problem in either one of the models is inconsistent. and we can now identify and document this. And this is automatically run after having thousands and thousands of components. That's where smart BIM automation comes into play. Then I want to show the expressions for beams, the top offsets. So let's do that. So that's an interesting one. So this is, here I'm now checking, this is where in the slideshow I'd shown you this, where it says a.the_z equals the z. So here you can see that it's identified those members where they're offset. You see they're clearly offset. Then I can say, well, that's too strict of a tolerance. So I'm going to come in and give it a 1-inch tolerance. So that reduces the number of members that fail, right? So there are more that are gray. So I still have an offset. So how did I write that expression or test? I'm saying the absolute value of the z bound of one component in one model minus the z of the other, the absolute value of their difference is less than 1 inches, right? So this gives me a lot of flexibility to kind of write this as I want. So these are kind of interesting ways to show you that. And let's conclude by just opening up columns. And under the columns, again, same type of thing where we have, our orphans, area tolerance. So if I turn on area tolerance, and we can, again, we're just isolating where we have problems, and I can see clearly there's a problem. This section is not the same as that section. I can go in and specify names and the descriptions. Now, this one gets picked up because obviously it's obvious that the area might be off if the name is off. And so again, here, these are all places where program, and I'm always just looking for color where I have the offset, right? So these are, we're finding all of these locations. Let's see if we have under columns any centroid tolerance issues. So centroid tolerance is a completely separate. So we're looking, again, we have a 2-inch tolerance set. So it's only these kind of members. It's a whole different set where it's identifying where they're the same member. Their representation might be different, but they're the same exact member designation, right? They're both HSS 4x4x3/8. So that's why it didn't trigger a fault before. It just happens that Tekla shows it differently than the other, but still our center line is too far beyond our tolerance. What I want to just say is, you can come in and kind of set these up as you wish. So I'm going to come in and we're going to do something on this model. This is our ETABS model. The section is defined here by this B. So I'm going to copy B, right? I'm just going to copy that variable. So it's section B. I'm going to go to operations, new, component matching operation. So I'm going to say, I'm going to limit this. This is the new one we created. We're going to limit it to columns only. So this is columns, right? So that's configuration number 1. We're checking ETABS against Revit. We're working with our ETABS model, right? We want to check the section B assignment in ETABS. So that's section B. We've selected that. So that's model A. So we're going to come in our expression and we're going to say A dot paste that variable equals B, because that's going to be our Revit model. So I come in here, hit tab. I've now switched over to, I actually need to turn on, both models are turned on, and let's see, we need to grab the other one. So this is our Revit model, and under Revit it's under the family, right? Because that's how we define sections in the family. I go here, that's under the B in family, copy that variable, go to our operation and say, so I'm now, let's review this. I'm saying in my ETABS model, which is A, the section property called B should be equal to my Revit model, which is B, in the family, the dimensions, which are classified as B. Those two should match. And if those two match, then I know I have the same exact component, right? That seems pretty simple. And we want to only show those where it fails. So let's run that. So we have 57 where those failed. So in this case, those were exactly the same. So these are, you can see these didn't turn yellow, but we actually found a few components where that's the case. And if we zoom in, we can see, in fact, Visicon helped us find. So this one here, B, is 2 feet. And if I click here and go to my ETABS parameter, it's 18 inches. Perfect example of how a simple relationship that we just defined was able to dig through thousands of columns and identify those sets that are still mismatched. As a project manager or even the author of models, and you just want to make sure that you have an effective way to quality control your own models, really great way to be able to do that. And all of this configuration, when you're done and you love what you're doing, and you say, hey, I want to share this with everybody else in my office, simply go in and say File, Save As, Template. And then all of this configuration, like this equation and everything else, automatically are saved. And then the next project you open up, you would say File, Apply, and just pull that template that you just defined. In conclusion, Visicon's component matching operation is really the smarter way to coordinate project models and goes beyond just classic clash checking that's available in most other BIM solutions. If you're interested, go to our website and download a free trial at visicon.com.